Okay, so good evening, guys. Almost all of you are there, right? Okay. So today it is aldehydes, ketones, and carboxylic acids, isn't it? Right? Are you guys there? Okay, I think I heard someone said yes. Okay, fine, cool. Okay, so do you want anything to know from this chapter and specific people, or we can directly go for?
Sir, name reactions.
Yeah, name reactions we will anyways do it while solving questions. So I think the only mechanism you have in this chapter is aldol condensation, isn't it? Is there any other mechanism you have? Do you have any other mechanisms in this other than
Sir, do
aldol?
we have mechanism for Cannizzaro, sir?
We do have mechanism for Cannizzaro. Like for every reaction we have mechanism, but in your syllabus, do you have in your NCERT textbook, have they given as a question? Have they given? I think they have given the aldol condensation mechanism. Have they given in the textbook?
Sir, I don't think so. There is mechanism for Cannizzaro and aldol condensation.
Okay, so any other mechanism have they given? I think Grignard, what is this? C double bond O with Grignard. I think this mechanism would have been there, but again, this is very simple, right? I have this attacking here and this going here, and this MgX attacks this carbon and hydrolysis. We spoke about this, I think, last class. Okay, fine. So I think there's nothing in specific. Cool. We will go for then questions. Okay, I just wanted to start with this. So when I compare hydrocarbons, right, with alcohols, or say I compare a hydrocarbon RH with an RX with an ROH, which is going to have maximum boiling point or melting point? A hydrocarbon, alkyl halide, alcohol, which will have higher boiling point?
Alcohol.
Okay, why?
So there is hydrogen bonding involved.
Obviously, right? So that is the answer you should give. Okay, so there will be a question like this. Alcohols are having more boiling point, the corresponding alkyl halides, right? The reason is this alcohols are capable of forming hydrogen bonds. Now, how will I show it is very important, right? Say I have ROH, right? I have another ROH molecule. I'll write it like this. Okay, H is done, right? Now, what you can understand is I have a lone pair on this oxygen, right? So this hydrogen is going to have a del positive and this is going to have del negative. There are two ways of looking at it, right? So you can either say that this is del negative, del positive. So del negative, del positive will have an interaction like this, right? Or you can even say that this del positive is going to have an interaction with the lone pair on oxygen, right? So either way, like this is how you represent the hydrogen bond. Right. So obviously, other than the normal van der Waals forces and stuff, if you have an extra dipole-dipole interaction like this, right? Obviously, the molecules will be little tightly packed, right? So if you want to convert them into the vapor phase, first you have to move them far away from each other. Obviously, in the gaseous phase, the molecules are very far away from each other, isn't it? Right. So because of this extra hydrogen bonding coming, you have to supply more temperature for them to move apart and then go into the gaseous phase. Okay, right, fine. So what about aldehydes? Say, what about if I compare it with aldehydes? Are they capable of forming hydrogen bonds, or say ketones for that matter? Are they capable of forming hydrogen bonds? Yes, no. Yes, what's your guess? You can be correct, you need not be correct, right? What do you think?
Yes,
These Okay, so someone says yes. So the next question is, will they be able to form, say, if I have one aldehyde molecule, right? Is it capable of forming hydrogen bonds with another aldehyde molecule, just like how you have in
Sir,
alcohol?
it's not
One
possible,
alcohol.
sir.
Okay. So it's not possible means you're telling that one RCHO, another RCHO, hydrogen bond is not possible. Is that what you're telling?
Yes, sir.
Okay. But hydrogen bonding is possible, not with another
water
aldehyde.
I think is possible.
Absolutely. Right. So
The
what you have to
oxygen is
understand.
not directly attached to hydrogen, no, sir.
Correct. Exactly. That's the point, right? You need to know some basics about hydrogen bonding, right? So if at all you need, what you have to understand is for hydrogen bonding, there should be something called as hydrogen donors, right? And I have something called as hydrogen acceptors. And if these two are there, yes, hydrogen bonding is possible. Okay, so what do you mean by a hydrogen donor? Just like you said, I should have a hydrogen atom attached to a highly electronegative atom like oxygen, fluorine, or nitrogen, right? So if that is present, yes, one of the criteria is satisfied, right? Second thing, for anything to be a hydrogen acceptor, there is only one criteria, that is that molecule should possess a lone pair. LP represents lone pair. Okay, right. Now you see here in this case of alcohol, you have a hydrogen directly attached to an oxygen atom which is highly electronegative. So one criteria satisfied, a hydrogen donor, right? Another thing is that you have a OH, or this oxygen is going to have a lone pair on this oxygen. So then hydrogen acceptor capability is also there. So one molecule itself, right? You have both hydrogen acceptor and hydrogen donor, right? So this happens like only if a particular molecule is capable of forming, able to have both hydrogen donors and hydrogen acceptor capabilities. Those molecules will have higher boiling point, right? But if you see, if you look at this or this, yes, you have lone pair on oxygen. Yes, here you have lone pair on oxygen, but there is no hydrogen donor capabilities, right? There is no hydrogen donor capabilities because you don't see, where this hydrogen atom is attached. This hydrogen atom is attached like this, right? So the carbon is not that electronegative, right? So hydrogen donor capabilities are not there. But if I take acetone, for example, CH3, C double bond O CH3, right? Now when I try to dissolve it in water, they will dissolve, right? But if I take a hydrocarbon, say I take CH3, CH2, CH3, I take propane, the what is that? Homo oligomer. Anyway, you don't have to worry about the keywords. So if I take a hydrocarbon, corresponding hydrocarbon, this if I dissolve in water, this won't react. This won't dissolve at all, right? Again, the reason would be hydrogen bonding. Right now, even though it does, this molecule acetone doesn't have any hydrogen donor capabilities, but still it can have hydrogen acceptor capabilities. And the hydrogen acceptor, sorry, this can be a hydrogen acceptor. It doesn't have hydrogen donor capabilities, but water molecule is going to provide that, right? So if you want to represent it, this is how you can represent C double bond O, two methyl groups. I have HOH water molecule. So I have these two interacting together, so that now you have a strong solute-solvent interaction, right? So whenever you have higher solute-solvent interaction, the dissolution process or the solubility will be higher. Okay, so these are all some things we didn't discuss in the previous things, regarding solubilities, regarding boiling points, melting points. Right? So just give you a direct picture, right? Fine. So, okay, fine. Now, what about these two? I have an alkyl halide, right? And I have an alkyl, hydrocarbon, which will have higher boiling point. When I compare a hydrocarbon and alkyl halide, it doesn't have any hydrogen bonds. These two doesn't have any hydrogen bonds. So one of the criteria is hydrogen bonding for boiling point or solubility, right? What are the other criteria which you have to look for?
So van der Waals force.
Yes, we have to look at van der Waals force. Okay. So how will you compare the van der Waals force of this, the van der Waals force of this? How will you compare? Van der Waals force generally depends on what?
Molecular mass.
Yes. Okay. One is that. Next one. One more is there. Okay. So if you give me that. Okay. So what I'll directly give you a formulation. Boiling point or melting point is directly proportional to the molecular mass. Okay. Definitely. Right. So what I give you a set of molecules. You just calculate the molecular masses, whichever is going to have higher boiling point. Sorry, whichever is going to have higher molecular mass, that is going to have higher boiling point or melting point. That is okay. Right. But say, what if I give you this and this? Right. Now, what you understand is there are 4 carbon atoms, so some number of hydrogen atoms, same number of carbon atoms and hydrogen atom. Basically, they are isomers.
So boiling point decreases with branching, sir.
Yes, that's the point, right? Okay. So these two are isomers. Can you tell me what kind of isomers are these? Specifically, can you tell me what isomers are these? There are different types of isomerism, right? What isomers are these?
Geometrical isomers.
For geometrical isomers, I should have
Positional, sir.
Okay, wait. I'll come back to the positional. Now you see that I have a C double bond C. There you can have cis, trans, and all these things. Those are what are called as geometrical isomers. Here, someone said position isomers. No, they are not position isomers. Right? What can be position isomers? Butan 1 all and butan 2 all. Say first carbon atom having OH or the second carbon atom having OH. Only if the number is different. But what is different is the number. 1 all, 2 all. Those are position isomers. Positions of the position of the functional group is different. Yes, Aditi, it is chain isomers. Okay. So what you have to understand is if there is a difference in chain length, in the sense that if you're going to write the name of this compound, you'll write the word but, right? But if you're going to write the name of this compound, you will write prop. Right. So whenever you see a difference in these root words, when I say root word, meth, eth, probe, but, hex, all these things, right? So those are what are called as root words. Okay. So whenever you see they have same molecular formula but different root words, they are what are called as chain isomers. Okay, right. So as someone told, I said that the boiling point or melting point is directly proportional to molecular mass and it is inversely proportional to branching. More and more branching, less and less would be the boiling point. Okay, so when I compare these two, this is going to have more boiling point than that. Because it has less branching, it has one branch. Okay, now there are reasons for this. Van der Waals forces decreases when I have branching. Like that's what you need to understand. Okay, fine. So these are all some basic things. Okay. Right. Cool. Fine. I'll ask you one more question. So if I have a phenol and I want to convert it into this one, what are the reagents which I have to use, or is there any name for this reaction? We didn't discuss it last time because it's a very important reaction, but we have to discuss it, right?
So Reimer-Tiemann, sir.
Yes, right. This is Reimer-Tiemann reaction. What are the reagents?
CH3 and NaOH.
Yeah, right. Chloroform and KOH, right? So you have to use CHCl3 plus KOH. Okay, very important. So this is what is called as, any common name for this?
Salicylic.
right? This is called salicyl aldehyde. Salicyl aldehyde. Please bear with my handwriting, people. Okay, right. So that is what is called as your salicyl aldehyde. So if I have, instead of the CHO, if I have COOH, then what is it called as?
Salicylic acid.
Yeah, salicylic acid. So can you tell me where, in which industry this salicylic acid or salicyl aldehyde is used? It is given in the textbooks.
Medicine, sir.
Yes, medicine. Any particular drug name can you think of?
So methyl salicylate.
Okay. What is it used for?
Aspirin.
It's used for removing pain, sir. The
Yeah.
methyl
So the
salicylate.
perfect. Yes, correct. They are pain relievers. They are fever suppressors. All these things. So generally, it is used in aspirin tablets, right? Painkillers. Okay, the salicyl, the derivatives of salicylaldehyde, you said methyl salicylate, something, right? So all these are used in aspirin preparation. Aspirin as a painkiller. Okay, fine. So these are all some things we didn't discuss last time. Okay, fine. Go to the chapter which we are now interested in. Okay. Okay, yeah, fine. So we'll start with one naming, which is definitely I expect a wrong answer from you. Now only I'm telling you. Let me see if you give me a correct answer. Okay, so I have this one. What is the IUPAC name of this compound?
Cyclohexanol.
Okay, fine. So what we expect is cyclohexane, and that's what we expect. But no, this is wrong, right? Okay, fine. Now why is it wrong is the question, right? See guys, you have hex here. That means how many carbon atoms?
6.
If I say hex, generally it is 6. How many carbon atoms are there here in this molecule?
Sir, is it
Oh, so it's cycloheptanol.
carbon
Wait.
carbaldehyde?
Wait. So it is not cycloheptanol. Someone is telling something else. Yes, what is it?
Sir, is it cyclohexane carbaldehyde?
Yeah, that's the correct answer. Okay, fine. So it is, you cannot put it as cycloheptanol, right? Only cyclohexane group is there. How will you put cycloheptanol? Cycloheptanol means I should have a 7-membered ring, right? So how you have to address these kind of questions is you are not going to use the prefix or suffix as al. You generally write al, pentanal, propanal, like that, right? So now you are not going to use it. So when you have to use this kind of stuff is when you have a ring or when you have a chain, and in that chain, the CHO molecule or say the C double bond O, if you are not able to incorporate it in the main chain, see, this is the main chain here, this is the main ring here, cyclohexyl ring is the main ring, right? But you see, the CHO is not anywhere in the ring, it's like a branch, right? So whenever you have these kind of problems, at that time, you will go for the the suffix as carbaldehyde. So the name of this compound is cyclohexane carbaldehyde, right? Cyclohexane carbaldehyde. You have to use this one. Whenever you are seeing that the CHO group is like a branch and you are not able to include it in the main chain, right? You have to use carbaldehyde. Okay, right? Same thing will go if I have COOH. If I have COOH, again the same problem. You cannot call it as cyclohexanoic acid. No. Again, you will account for, you will miss one of the carbon atoms, right? So again, what you have to do? You should write cyclohexane. Instead of carbaldehyde, you should write carboxylic acid, right? So the name of this compound would have been cyclohexane carboxylic acid. Okay, right? So this kind of stuffs will be asked to you, right? But if I have something like this, then what is the name of the compound? For this compound, what is the name of this compound?
Cyclohexanone, sir.
Right? Cyclohexanone directly. Now you see there are no problems as previous case. There are only 6 carbon atoms and the C double bond O is in the ring. Right? So normally how you do this is going to be called a cyclohexanone, ONE. That is a ketone. Okay, so this point I wanted to specify to you. Okay, fine. Cool. See guys, at least one question you will get in with respect to IUPAC naming. Please be very, very careful. Okay.
Sir, could you just
Yeah.
explain the nucleophilic addition reactions once?
Sure. Right. Okay. So one of the classes of reactions, your aldehydes and ketones or any carbonyl compound generally undergoes is nucleophilic addition reaction. Right. So we already spoke about this. When I have C double bond C and when I have C double bond O, both of them can undergo addition reactions. Right. But in case of C double bond C, it is going to be an electrophilic addition. Right. And in case of C double bond O, it is going to be a nucleophilic addition. And I told you the difference. Why is it called like this? Anyway, does anyone remember? Why is there a difference? Both are addition reactions and one is called nucleophilic, the other one is called electrophilic. Why?
Sir, it's because in nucleophilic addition, nucleophile is attacking. In the other case, the electrophile is attacking.
Yeah, right. It's all about which attacks first, right? So in case of nucleophilic addition, nucleophile attack first. In case of electrophilic addition, electrophile attacks first. Right. Okay. So if I look at any nucleophilic addition in case of C double bond O, like I can give you the general mechanism. So this is a nucleophile coming. So you see this carbon atom is going to have a positive charge, a partial positive charge, because oxygen is more electronegative. That will have a partial negative charge, and the carbon and carbon is going to have a partial positive charge. Right. So the nucleophile attacks, and then what will happen? You will have the nucleophile here, other bond, and this bond would have broken. So you will have a O minus. Say if I have a H in the molecule, the O minus will take up the H. That's very simple. It's from OH. Okay, right. Now there are so many different reactions. Say I can add the nucleophilic addition reaction can be in the form of HCN, the cyanide molecule will attack. Then the H plus will be taken by O minus to form cyanohydrins, right? Or I can even go for RNGX. We already saw this. R minus will attack, right? So how will you hope you know how we represent it? R minus NGX plus, same mechanism, right? Or I can have any other nucleophile. I can even have ammonia. How ammonia? You have ammonia as having a lone pair, so this will go attack the carbon, and the same thing will happen, right? Or you have ammonia derivatives, right? Ammonia derivatives. I will write it as NH2Z. Like you see ammonia here, right? You just remove one hydrogen and put some other group. That will become what is that? Ammonia derivatives, right? So you have so many ammonia derivatives, right? Say first thing is say the Z can be R. That means if I have say NH2R, this is a primary amine, isn't it? Right? So again, primary amine will react and all that, right? Or I can have something called as hydroxyl amines. So this is what is called as hydroxyl amines, right? So hydroxyl amine again will react. So the thing is, guys, right? In your NCERT textbook, they would have given you a table, especially for this, especially for ammonia derivatives, right? Okay. Now I just give you the shortcut for remembering this. I think you'll already know this, but still I'm telling you, right? So when I have a C double bond O, right? And I have this NH2Z, Z can be anything, right? Now, how will you remember the product? It's very simple. You just remove this H2O and you write C double bond N is it. As simple as that. Okay, so you have a C double bond O and you have an ammonia derivative that is like NH2Z, right? So you don't remove the water molecule, H2 from N and O from carbonyl compound. You have a double bond, so you make a double bond with nitrogen. So this is what is going to be the product. Okay, so now what you have to remember is what are the names of the ammonia derivatives, right? And what is the name of the compound formed? Let me ask you this. If the ammonia derivative was hydroxyl amine, that means here I would have had OH in the product. What are these compound called as?
Oxymine.
Yeah, not oxime. It's called oximes. Oximes. Right? It's called oximes. Right. Say another thing. If it was NH2 ammonia derivative, what is the name of the ammonia derivative, guys? NH2. NH2 is called as what?
Hydrazine.
Good. Right. It's called hydrazine. Okay. So if this forms the compound and this Z would have been NH2, right? So you'll have C double bond N, NH2 will come. What is the name of that compound?
Hydrazone.
Absolutely. Right. Hydrazine will be the ammonia derivative. Hydrazone will be the compound name, the product name. Right. So like this, you'll have semicarbazide, semicarbazone. Right. So like this, you'll have 5-6 things, right? In your NCERT textbook, they have given you a table, very important table. Okay. All the ammonia derivatives names along with the product's name, along with how the product looks, you have to remember. It's very simple. If you can remember this one, only thing you have to change is the Z, nothing else, right? And you have to remember the names. That's it. Okay, right. Okay, cool. So that's about ammonia derivatives. We saw about HCN. We saw about what else we saw? Grignard reagents, right? Now there is one more thing. There are still more things that undergo nucleophilic addition, right? That is alcohols, right? So when I have a C double bond O, right, I can even have an alcohol acting as a nucleophile. How? Mechanism is very similar. You have the lone pair, attack here, this will go back, right? So what will be the compound formed? You have CO minus, let me put it as OH, right? Say I have this H, which is here, right? Which is going to attack me, which is when I'm going to remove it and put it as O minus, that H will attack here. So that is not a problem. Okay, right. So COH, and you have 2 more bonds, and what is remaining? OR dash. What are these compounds called as, people? When you have a carbon atom, when you have a single carbon atom having one OH and one OR, what are these compounds called as?
Hemiacetal.
Absolutely, right. These are what are called as hemiacetals. Right. Now, if you're going to use this in excess, right? If you're going to use this in large amount, say this is 1 mole, this is 10 moles, or something like that, right? This is, if you see the stoichiometry is 1 mole of this requires 1 mole of this to form hemiacetals, right? So I use 1 mole of this and 5 moles of this. So the reaction is not going to stop here. The reaction, I have, say, another ROH, R-OH coming. And in this case, it is not a nucleophilic addition because it is not anymore a carbonyl compound. So what kind of reaction do you expect here?
SN2, sir.
Yes. So I expect a nucleophilic substitution. Absolutely true. Right. So what is going to happen? This OH is going to get replaced by this R-O minus. Right. So you will have CO R dash O R dash, another 2 bonds. And these are what are called as? These are what are called as?
Acetals.
Absolutely. Right. These are what are called as acetals. Okay, so whenever you have one OH and one OR on the same carbon atom, see, not like you have one OH and 3 carbon atoms, so you have one OR and you call it as hemiacetal, absolutely wrong, right? You should have a single carbon atom that should contain OH as well as OR. Then it is a hemiacetal. Same way here, if you have two ORs attached to the same carbon atom, those are what are called as acetals. Okay, right. Now what you can like, I don't know whether, do you have cyclic acetals in your
No,
NCERT textbook? You don't have? Okay, so it's pretty simple. Maybe I'll tell you what is this. Very simple, right? Say now you have your carbonyl compound, right? Now you see you are using two molecules of this. Is it not? One molecule to undergo nucleophilic addition to form acetal, another molecule of this to undergo nucleophilic substitution, sorry, in this case hemiacetals, and one more molecule to undergo nucleophilic substitution to form acetals. Right. Now, what if I use something like this, CH2OH, CH2OH? My problem solved, isn't it? I don't have to use 2 moles or excess. I just have to use some amount of this glycols, right? Glycols are generally 1,2 diols. Okay, so it's very simple, right? What will you form is O, CH2, CH2, O, and a bond, and 2 more. Right? So you would have had one OR. If I just break this here, right? You'll have one OR. Again, take this here, you'll have one OR. Acetal basically, but in this case, it's coming from the same molecule. These are what are called as cyclic acetals. Okay, these are what are called as cyclic acetals. This is a very good protecting group. Oh, right. I don't want to go into the details, right? That's another level of chemistry. Okay, so fine. So these are all the different nucleophilic addition reactions, right? So someone asked it, is your doubt clear, Kana? Yes? No? Okay, fine. I hope it should be clear. If there's anything else, you can ask me. Okay, fine. And oh yeah, I forgot one thing here. What about the reactivity? Now we saw the mechanisms, we saw what are the different reactants, different products in nucleophilic addition. What about the reactivity? If I ask you, say I have HCHO, say I have CH3CHO, and say I have CH3, C double bond O, and CH3, right? And I ask you to arrange them in the order of reactivity with respect to nucleophilic addition. See, remember, right? One molecule can be more reactive towards one reaction. The same molecule might not be reactive towards some other reaction, right? So whenever we speak about reactivity, we should specify which reaction we are speaking about, right? So I am talking about nucleophilic addition reactions, and I'm asking you to decide the order of reactivity for these molecules. What will be your answer? Or if I put 1, 2, and 3, which do you think is maximum reactive here?
1.
Okay, why? Correct, your answer is correct. Why?
Because it
Steric
has
hindrance.
steric hindrance.
Okay, fine, steric hindrance. Fine. Okay, if cool, fine. Okay, I have to accept the answer. There is no other go because it's one of the reason is very correct. One of the reason is steric hindrance, guys. Right. What is the other thing which you look into? For example, if I have to make a really good compound, say I have CH3, CH2, C double bond O, CH3, right? And okay, I'll take it as 4. Actually, this doesn't work. Okay, cool. But anyways, one of the obvious reasons is steric hindrance. The nucleophile has to come and attack the carbonyl carbon, right? So if at all the groups are like there are so many bulky groups present, the nucleophile will find it difficult, right? The nucleophile will find it difficult to go and attack the carbonyl carbon. That is one of the reasons. So I can directly say the reactivity is inversely proportional to the steric hindrance here, crowdedness. All right, more and more steric hindrance, less and less would be the reactivity. Absolutely true. What is the other thing which you have to look at?
Electrophilicity.
Electrophilicity of
The carbon.
good, right? So you see, guys, I have a C double bond O, and as I already told you, this is going to have a del negative, this is going to have a del positive, right? So you understand, more and more is this del positive, right? More and more will be the reactivity because the nucleophile is coming, which is negatively charged, right? So more and more is the positive, partial positive, or in perfect words, as we said, the electrophilicity, right? So more and more is the electrophilicity of this carbon. More and more will be the reactivity, right? Okay. So another thing, it is directly proportional to the electrophilicity of the carbonyl carbon. Very important to specify this. Okay, it is the electrophilicity of the carbonyl carbon which decides the reactivity, right? Okay, now you look at this. Definitely, if you just use one of them in this case, you will be able to get the answer because the least sterically hindered is this, next sterically hindered is this, and this is going to be maximum sterically hindered. So this would have been, oh sorry, this side, right? This would have been the order of reactivity. Absolutely true, right? Now same thing can be explained with the help of this also, the electrophilicity of the carbon. Very simple, right? So you see, in this case, I have a H and a CH3. So it's all about the positive charge on this carbon, right? And we know methyl groups are electron donating in nature, right? Methyl groups are electron donating in nature. So obviously you will see that the positive charge on this carbon is going to get decreased because this CH3 is going to donate electron to this carbon, decreasing the negative positive charge. In this case, you see here the hydrogen doesn't have any effect. Same way, that's why you see this is more reactive. The maximum positive charge will be there on this carbonyl carbon, and then this carbon, and then this carbon is going to have the least positive charge. Again, for the same reason, because I have two methyl groups which are going to donate electron to the carbon. Right? So either way, either with respect to steric hindrance you see, or with respect to electrophilicity you see, you will almost get the same answer. But it's good to know both of them. Actually, this is a better reason to look at. Right? Electrophilicity is a better reason to look at. Fine. Anyways, okay. Next question.
Sir,
Yeah.
so could you also revise all aldol and cross aldol condensation?
Absolutely, absolutely. We'll do.
Yes.
Right. I'm really surprised by the thing that you do not have mechanism for aldol condensation. This is I don't know what should I tell. Okay, fine. It's very easy. Okay. Guys, I want to ask you one thing. You obviously would have known by this time that I teach a little extra stuff. Extra in the sense, what should have been taught by your NCRT school people, that should have been done because that's why they didn't do. That's why I'm doing. Do you have any problems like this? If I give you the mechanism, are you finding it interesting, or is it a burden for you? I want an honest answer, please.
Sir, it's interesting, so you can actually teach it.
Okay, fine. So I understand that even though, okay, good. It's good that I'm getting a positive response, because some of the students would be like, sir, we already have to study more. Now we are getting this also, right? So what I will tell them, if they tell me something like that, this is how you have to study organic chemistry, right? All the while, all the 2 years of organic chemistry I've been learning, people have been teaching you in a very wrong method, right? This is how, not only for this reaction, for any reaction you study, mechanisms are very important. If at all you would have been my student, that is how I would have taught you. Anyways, not a big deal at all, right? Okay, so we talked about aldol condensation. Very important reaction, right? Okay, Now, the reaction is very simple, but I wanted to concentrate little on, it's a very small mechanism, not a big deal, right? Fine. So the first question, why is it that the aldol condensation reaction occurs? Is the first question you have to answer, right? So the answer is aldol condensation reaction occurs because of presence of alpha hydrogens in carbonyl compounds. Obviously, we're talking only about aldehydes or ketones, or actually the aldol condensation reaction. I'll not call it aldol condensation, but same kind of reaction can be given by esters also. Esters we know. See, it also has a C double bond O, right? But in that time, it is going to be called not aldol condensation. It is going to be called as Clementine condensation. But again, we don't have to go into the details, right? So what you have to understand is aldol condensation is happening because of presence of alpha hydrogen, right? So now if I just give you this reason, there are millions of functional groups which are having alpha hydrogens. You just have to have a carbon with a functional group, and the next carbon should have a hydrogen. That is not the only reason, right? You have so many molecules, so many functional groups having having your alpha hydrogen, right? What is the speciality of alpha hydrogen in carbonyl compounds is the question you have to understand, right? What the answer to that is, this alpha hydrogens in your carbonyl compounds are acidic. Okay, are acidic in nature. Means what? They will be able to come out as H+. Okay, right? Fine. Now, how do I prove it? How is it that, okay, out of nowhere, I have never seen something like this. How am I going to prove it? It's very simple, right? Say I take a normal example. I have CH3, CH3, right? Now, this is my alpha carbon atom. This is my alpha carbon atom, right? So any of these hydrogens is what is going to be called as alpha hydrogens, right? Now, assume that I'm going to remove one H+, right? Now, we already spoke about the acidic strength, right? Now, tell me, guys, acidic strength, if I give you 2-3 compounds and ask you to decide the acidic strength, what is the criteria which you will use? We saw about it in alcohols, or in so many things we saw. How
the
do you
stability
decide?
of the conjugate base, sir?
Absolutely true, right? You have to first remove the H+, right? After removing the H+, you have to look at the conjugate base, right? If the conjugate base you see is stable, then I can say that, yes, that's a good acid. Same methodology I'm going to follow here. I am going to remove the H+, and I'm going to check whether the conjugate base is stable or not. Let me do that, right? So I remove the H+, minus H+, obviously from the alpha carbon atom. Please don't remove from anywhere else, right? If I can even have one more carbon atom, 1000 carbon atoms, but the carbon atom next to the carbonyl is what is alpha carbon atom. Please be very careful. Okay, right. So I have the H+ removed. So what will you have? CH3, C double bond O, CH2 minus, right? I'm telling you this is stable. Tell me, how is this stable?
Resonance, sir.
Beautiful, right? So you have this bond coming here and this bond breaking. Is it not? This is resonance, right? This bond coming here and this bond breaks. So I can write the resonance structure like this: CO minus CH2, double bond CH2, right? Now you see this conjugate base is stabilized by resonance. Okay, right? Like minus H+ means obviously you have to put a base here. You cannot just remove the H+, right? Okay, so anyways, so you understand that the presence of alpha hydrogens is the reason. And what is so special about the alpha hydrogens? Because these alpha hydrogens can come out as H+, because the conjugate bases formed here are stable. Okay, this is the reason. This is the only reason that your carbonyl compounds are able to undergo aldol condensation reaction. Okay, fine. We'll see the mechanism now. We understood what is the reason behind it. Any questions? And have you ever heard this term tautomerism? Yes, have you ever heard this term tautomerism? Definitely,
Yes,
you should have. Right. So you should have studied keto-enol tautomerism in your 11th class. Hopefully, you should have studied it, right? So what do you understand? Say this and this. If I just put a OH here, These two are what are called as tautomers. Okay, and the only the beautiful difference between other types of isomerism and tautomerism is that other types of isomerism, say if I give you a molecular formula, you will be able to write so many structures on paper, right? Say if I give you C4H10, you will write normal butane, some branched compound, all these things you will be able to write on paper, right? But if I have a test tube of N-butane, normal butane, in that same test tube, will I have the isomer of it? The answer is no, right? But tautomerism is something like that. It is going to happen in reality. Why is it happening in reality? Same reasons.
Equilibrium.
Absolutely, they will be actually in equilibrium. But again, equilibrium will be more towards the keto form, not the enol form, because enol form is a little unstable, right? But still, they will be in equilibrium. They'll be obviously, if I take a test tube, if I take a test tube containing acetone, right? And if you check for what other compounds are there which are present in that particular test tube, you will find that this compound is also present, but minimal amounts, where you say 1%, 2%, right? But still it is present. Why? Because it undergoes this kind of transformation. The H plus is removed, and then this goes, O minus is formed, again the H plus attacks here. This happens in reality. Okay, so anyway, so that is the same reason why tautomerism exists, again because of acidic alpha hydrogen. Why aldol condensation happens? Same reason. Okay, fine. So now we look at the mechanism. Right. Okay. So obviously, the only condition which is required for aldol condensation reaction to occur is presence of alpha hydrogen. Okay. So if I don't have alpha hydrogen, aldol condensation will not occur. That's it. As simple as that. Right. So let me take an example. So let me take a simple example. Okay. CH3CHO. I have. Right. Okay. Now generally, what they do is they go for dilute NaOH. Right. That's what they do, but you don't have to use always dilute NaOH. I can go for any kind of base, right? Generally, we prefer organic bases, right? Again, I don't want to go into the details, right? Generally, we use so many organic bases. If at all you want some examples, there's something called as LDA, so many stuff, pyridine, all this stuff can be used. But again, for in your book, they have given only this. But again, for any of the bases, the mechanism is very similar. The role of the base here, the role of NaOH here, is just to abstract the hydrogen, the alpha hydrogen, because if it is not there, H plus cannot come out, right? Okay, so what you have to understand is first thing, the H plus comes out, and remember this is the alpha hydrogen. Do not remove hydrogen from this. The alpha hydrogen is this, right? So what will you form? CH2 minus C double bond O H, right? Now you have this with you. Okay, obviously you would have remembered that you have to use two molecules of this, right? So you have another molecule, CH3, CHO, and now this is going to be a nucleophilic addition reaction. Okay, first step is removal of alpha hydrogen. Second step is nucleophilic addition. We already studied nucleophilic addition. What is going to happen? This negative charge will come and attack this carbon, and the double bond O breaks, right? So what will happen? Say if I just concentrate on this, CH3, CO minus, and the H is there. And what is there? Next comes CH2, C double bond O, H. Okay, right? Now, obviously, now you have the O minus, you remove the H plus, you just add the H plus, OH, right? Now, this can undergo dehydration. Dehydration is OH from this and H from this carbon. So basically what is going to happen is, okay, first to take this down, I'll tell you. This is the mechanism. Mechanism is very simple. Remove the H plus, make the carbanion, nucleophilic addition of the carbon to carbon. You take the second molecule of the aldehyde or ketone, then you attack it, right? So this is the compound. So remember, whenever aldol condensation reaction happens, you will either get beta hydroxy aldehyde or beta hydroxy carbonyl compound, right? You'll always get beta hydroxy carbonyl compound. Very simple, right? This is the main carbon atom. This is the alpha carbon atom. This is the beta carbon atom. Not only in this, any aldol condensation reaction for that matter, right? You have to get a beta hydroxy aldehyde or ketone, or Now I told you this is going to undergo dehydration. So, or it can form alpha beta unsaturated aldehyde or carbonyl compound, right? Carbonyl compound, right? So either it forms beta hydroxy carbonyl compound, that is aldehyde or ketone, or it will form alpha beta unsaturated. That means what? Between the alpha carbon atom and the beta carbon atom, there's a double bond, right? So either this or this alpha beta unsaturated carbonyl compound will be the product. Okay, fine. So now you have taken down this, right? Now you see this this alpha carbon is still having a hydrogen atom, is it not? Right, it still has a hydrogen atom. That means it can still come out as H plus, right? So if I go for one more mole of OH minus, OH H from this, H plus from this, obviously OH minus from this will leave, right? So what will happen? I will have CH3, CH double bond, CHO. That's C double bond OH. I wrote it as CH. Okay. Now this is also very simple, right? H plus coming from this, right? If if or not, I can give you the mechanism also. Very simple, right? So you remove the H plus, right? I'll just write it as CH minus. Okay, and this H plus attacks this oxygen. Assume like that. So you'll have OH2 plus. Now what will happen? This bond will come here, and this OH2 will leave. Okay, you don't have to remember the mechanism now, right? If you can remember just the first part, right? The formation of the carbanion, and that attacks the nucleophile. Say that attacks the carbonyl carbon and forming this. That much you remember. And then you just write minus H2O. You don't have to put anything like this. You put minus H2O, and you write this compound. That's it, right? But the mechanism is also very similar. I have this itravine CH2, and this is an alpha carbon atom of the carbonyl carbon. So that can again come out if I use OH minus, right? So that will, again, you can just assume it like, I know OH is a very bad leaving group. We already spoke about it, right? That is why I just removed the H plus and I added the H plus here so that it becomes a good leaving, right? So this will attack here and the bond breaks, C double bond, CO bond breaks and the H2O leaves. Done. You are going to make a double, right? Okay, right? So this is the whole mechanism of aldol condensation reaction. Now what you see here is you are using two molecules of the same stuff, right? What if I use one molecule, one mole of one carbonyl compound and another mole of another molecule, another carbonyl compound? That is what is called as your cross aldol reaction, right? Okay, now before we see cross aldol reaction, I want to give you a shortcut, right? Shortcut for remembering the compound. You should remember the mechanism. Very, very helpful it will be, even for your JEE mains if someone is writing, or NEET exam if someone is writing, it will be very helpful, right? And now if at all you want to know the shortcut of predicting the product, that I'm going to give you now, right? Okay, let me do that. Any questions here in this mechanism?
Clear, sir.
Okay, I suppose it is clear. If there anybody has any doubt, please stop me and ask. Okay.
Yes, sir.
Yeah, good, good, nice. Okay, so now I'm going to give you the shortcut for remembering the compound, right? So I write CH3, C double bond O, H. I write it like this. One O pointing towards that side. I keep it like this. Okay, now obviously you're going to remove alpha hydrogen, and from the mechanism you understood that two hydrogens from the alpha positions are removed, right? So how you write the next compound is like this. You write it as H2CH Why am I writing like this? Because this is the alpha carbon atom, right? Now this alpha carbon atom from these two hydrogens are removed. What you do is just remove this water molecule. You are going to get the same stuff what we discussed last time with the help of the mechanism. Okay, so how do you remember? You make sure that the oxygen is pointing towards this side, and the next molecule when you write, two hydrogens of the alpha position should point towards this side. Remember, alpha position. Do not, if you're gonna write, take some other position and do it, problem is wrong. Right? So you take the alpha hydrogen, remove the water molecule, and you are going to get this aldehyde. alpha, beta, unsaturated aldehyde. You see, alpha position, beta position, having a double bond. Okay, fine. So now we'll look into the cross aldol reactions. Okay, mechanism is very similar, people. Mechanism is not similar, exactly same, right? Say I use CH3CHO with CH3CO, CH3. Okay, first tell me how many products, if I just put this and dilute NaOH, how many products do you expect?
4.
Good. Can you tell me how 4 come?
First condensation products of each, and then cross condensation product of.
Okay, right? So obviously, okay, self aldol of this, right? And self aldol of this, 2 products. Now, next thing is obviously cross aldol is going to happen, but you have a doubt there, isn't it? What, so how floatal 4 is correct, right? Self aldol of this, self aldol of this with 2, right? Now, next question is, if I'm going for cross aldol, which is going to act as a nucleophile and which is going to act as the electrophile? That's the question. This can act as nucleophile, this can act as electrophile. Same way for this can act as nucleophile, this can act as electrophile. What do you mean by electrophile? Electrophile is basically after removing the H plus, the carbanion which is getting formed. That is a nucleophile. What is the electrophile? The C double bond O which is there, it is going to get attacked by the nucleophile is what is my electrophile, right? Okay, fine. So what I want you to do is forget about, okay, you write all the 4 products. Go for it. I'll give you maybe 2 minutes. Use the shortcut. I told you, right? Use the shortcut and tell me all the products. 4 products. Go for it. Use a shortcut. I told you a shortcut. Remove H2O. So when it goes to cross aldol, where you're removing hydrogen, where you're removing oxygen, depending on that, you'll get 2 products, isn't it? Okay. I hope everybody is trying. Please do not sit idle. Okay, fine. So one of the products we already saw, the self aldol of this would give me first product CH3, CH double bond CH, CHO. And if I go for self of this, I would be having CH3, C, H, H will be there. No, H won't be there. Right? C, CH3 double bond CCH3. What is happening? Okay, correct. Right? Then you will have C double bond O, CH3. This is a second product, self aldol of this. Okay.
Sir, the second product, another CSC won't be there, right, sir?
1, 2, 3, 4, 5, 6, 7. I should have only 6 carbon atoms. Where am I getting one more?
Sir,
Maybe if I-
double bond CH,
wait.
sir.
Wait. Let me do it normally. So I have C double bond O, CH3, CH3, and I have H2, CH, C double bond O, CH3. I remove this. So you will have CH3, C, CH3, CH3, C, CH3, double bond, yes, CH. Correct. Yeah, this is the correct answer. Okay, this is a self aldol of this. Okay, fine. Now cross aldol of this. Say, let me remove oxygen from this, hydrogen from this. Okay, let me, so I can, okay, if I just directly do it. So third one, oxygen from this, hydrogen from this, CH3, CH double bond,
Cross aldol can be
CH.
any order, right?
Sorry.
So the cross aldol can be in any order, right?
Any order. Nobody, no, that one doesn't matter. But you have to get the product. 2 products. I mean, cross aldol, 2 products that you have to get. Right. So this is third product. Oxygen from this, hydrogen from this, and the opposite. Oxygen from this, now hydrogen from this. I don't have space. Let me write at the top. So fourth one is hydrogen from this, oxygen from this. So like if I start from here, oh sorry, okay, let me write it maybe. So CH3, C double bond O, CH3, H2, CH, CHO. Remove this. So what will you have? All you have is CH3, C, CH3, double bond, CH, CHO. Right? So all these are the 4 products. Very simple. All of them mechanism exactly same what we saw. But now you told me that the mechanism is not there in any study textbook, so you don't have to worry about it, right? So you can easily get the 4 products out. Okay, I have something else also. I have something called as intramolecular aldol, right? It's something like cross aldol. In cross aldol, you use 2 molecules of 2 different aldehydes or ketones. But say in the same compound, what if I have 2 carbonyl carbons? Something like this: CH3, C double bond O, CH2, 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 C double bond O, CH. Something like this, right? Now you don't need to use two molecules or one, or you have to use just one molecule in the base, right? What will happen? Same thing. Say the alpha hydrogen is this, or say the alpha hydrogen is this. This might attack here, or say this might attack here. You will always end up in a cyclic structure. Anyways, it's not there in your syllabus. So let's see this next information. These are what are called as intramolecular aldol condensation reactions. What do you know? What is intramolecular? Within the same compound, right? Okay, so that is about what is that? Your aldol condensation. Okay, I hope it's clear. And any other questions? Any other thing which you want me to revise?
Sir, just the named reactions one, sir.
Okay, fine. We'll just look into it. But name reactions, it's like I'm gonna give you the name reaction. I mean, I'm gonna give you the name and the reaction. That's what we have to do. Like, I don't see anything else happening. But anyways, since you have asked for it, okay. First, I can just talk about Clementine's reduction. Okay. Now, tell me what this does. What is the reagent? I mean, what is the reactant and what is the product? Clementine's reduction.
Reduction of carbonyl compound to CH2 group in the presence of zinc amalgam and concentrated HCl.
Zinc amalgam. Okay, correct. Right. Okay. So if you have a C double bond O, right, and if you go for zinc amalgam, this is how we represent zinc amalgam. Okay. Tell me, guys, what is an amalgam generally? What is an amalgam?
Mercury, sir.
Okay, mercury is there. Amalgam means mercury will be there. What exactly is this? Okay, so basically amalgam is a solution, right? So in a solution, I know I have solute and a solvent, correct? So in an amalgam, mercury acts as solvent. That's the whole point. Okay, you dissolve something in mercury. So zinc amalgam means you dissolve zinc in mercury, so liquid. That is what is called as zinc amalgam. Mercury, sodium amalgam, magnesium amalgam, all these things. Amalgam means there's a solution in which mercury acts as solvent. Okay, so anyways, so I have zinc amalgam. In the presence of HCl, you are going to form C, H, H, and 2 more bonds. So conversion of C double bond to CH2 is what is going to happen, right? So for example, if you have CH3, CH, or something like, if I have double bond O, and if you're going to put the same thing, you are going to get this molecule as the product. Okay. Now, similar way, I'll be able to convert the same thing with the help of second name reaction. What is that? Same thing, reactant product same, only the reagent is different. What is the name of the reaction?
Wolff-Kishner reduction.
Yes, absolutely true. So you have Wolff-Kishner reduction. Same thing. You have a C double bond O. You convert it into CH2. Right? Now here the only thing would be, here you have to use what?
Hydrazine.
Good. You have to use hydrazine, NH2 in the presence of H2O2. You have to use, I don't think you're able to see it, but still okay, right? So you have a hydrazine and a hydrogen peroxide, both of them to be used to get the corresponding hydrocarbon. Okay. Okay, that is about Clemenson's and your Wolff-Kishner, right? Now you have, I think, okay, you have something, I think, Stefan's reduction. Right? What is Stefan's reduction, people? Do you have Stefan's reduction? I think you have, right?
Yes, sir.
Yes, sir.
Yeah. So what happens in Stefan's reduction?
Nitrile compound is converted to aldehyde.
Absolutely. Right? Fine. So if you have a RCN, you convert it into RCHO. Okay, fine. What is the reagent here?
SnCl2.
Absolutely true. Right? You just have to use tin chloride, SnCl2.
In the
You'll be
presence
able
of
to.
HCl. Sir.
Absolutely, absolutely. Yes, you have to use a H plus. Okay, HCl is generally used, right? So you have SnCl2 converting to RCHO.
So we can use any acid, sir, like
Any acid, no problem. Yes, any acid. But try to follow what is given in textbooks, right? I don't know, like this NCRT people, right? They have so much ego, right? So yeah, so you just make sure what they use, but generally,
instead
yes,
of any acid, we can just get H plus now, sir.
Any acid gives me H plus. Yes, good enough for me. Yeah, but please use only HCl, even though it's logically correct. I don't know whether they'll give you a mark or not. You put generally HCl. It's better.
So
Okay,
for
but
any other reaction, like if it involves any acid, we can in general write H plus, right? Like
yes,
if
yes,
if
yes.
it's further or something.
Yes, you can do that. You can do, like, generally it doesn't matter what kind of acid you use, right? Generally, but it depends on the reaction whether I want a strong acid or a weak acid. That and all matters. But again, for your level, it doesn't matter at all. So even if you just put H plus, it should be sufficient. But again, just for you to not lose a half mark or a quarter mark, you include whatever is given in the textbook. Okay, I am really feeling bad that I'm telling you this, but that's how the system works. Okay, so whatever is given in textbook, please follow that. But again, logically speaking, just writing H plus is sufficient. Even if I go for PhD level, right? When I write my exams for my college, I write like this only. I just write H plus, and they're okay with it. Okay, anyways, right? So that's about Stefan's reduction, Clemenson reduction, Wolff-Kishner reduction. Any other reduction do you have? Rosenman reduction I have. Rosenman reduction comes in this chapter.
Yes,
I'm
sir.
not sure. Okay, in this chapter only. Okay. Rosenman reduction. Okay, what happens here? Okay, first. Okay, fine. You tell me what happens. Rosenman reduction. What
Acyl
converts
chloride to aldehyde.
Sorry.
Acyl chloride to aldehyde.
Absolutely right. So, or you can generally tell acid or any acid derivative, RCOCl, right, to an aldehyde. Basically, you form RCHO. Okay, what is the reagent?
PDBaSO4.
Yes, right. Not just PD with the presence of BaSO4. You have to use hydrogen in the presence of palladium poisoned with BaSO4. That's what is very important. Palladium is the catalyst. H2 is the reagent. Palladium is the catalyst. BaSO4 is a poison. Not poison like which we eat that is really harmful for us. Not that kind
Catalytic
of poison.
poison.
Correct. Absolutely true. You used to study it in surface chemistry. Correct. So there will be something called as promoters. There will be something called as poisons. Promoters increase the activity of the catalyst. Poisons decrease the activity of the catalyst. So BaSO4 is a poison here, which will decrease the activity of palladium. Right. So to give you the product, very simple. Right. And it's not necessary that I have to use only RCOCl, guys. But again, I'm not sure how this thing works. Generally, it will work for acids also. I've done this in lab and have looked at it, right? So this will work for acids also. But again, do not take any chance. You write only acid chloride. Okay, fine, good. So I think these are the different reduction reactions. And with respect to name reactions, I think, right, Stephens, any other reduction you have? No, right? I don't think you have any other reduction present. Okay. Cannizzaro is very important. Next, go for Cannizzaro. Cannizzaro mechanism is a beautiful mechanism, but again, this is not there in the syllabus. We will not look into it because this is too much for you. Okay, there are a lot of questions which will come, sir. Why this? Why that? Right? I am ready to answer, but we don't have time for that. Okay, so generally we'll just look at the reaction alone. Right. So what you have to understand is you have to understand that there should be no alpha hydrogen, right? Because the reagent is a base. NaOH, same NaOH as you use in the case of your Aldol condensation. That's what you use here. But here, there should not be any alpha hydrogen. Only then it will give Cannizzaro, right? And the best example would be either HCHO, because it doesn't have any alpha hydrogen, or you can even go for benzaldehyde. That is what I think we'll give you in a textbook. Okay, anyways, so now again, same thing. Now in this case, instead of dilute NaOH, I have to go for concentrated NaOH. That's the only difference here. Okay, so this is like a disproportionation reaction. Okay, what do you mean by disproportionation? Anybody knows? Have you ever heard this term?
Oxidases and reduces at the same time.
Okay, oxidizes and reduces at the same time. There are a lot of reactions where oxidation and reduction happen simultaneously. But how, like, I know you're trying to say something else, but your wordings are wrong. So what you have to tell is same compound. One compound oxidizes, the same compound reduces. That is what is called as a disproportionation. Okay, there's only one compound. This compound oxidizes, this compound reduces. But if it's a normal redox reaction, reduction oxidation reaction, one chemical substance will get oxidized, other chemical species will get reduced. That's normal oxidation or reduction reaction. Now here it is same compound undergoing oxidation and reduction. Obviously, we know that when it undergoes oxidation, it is going to form acid or say the salt of the acid. Now, depending on what base you use here, if you're going to use KOH, you'll put K. If you're going to put NaOH, you'll put Na. Say COONA, and the other one would be CH3OH, alcohol. The reduction process would be alcohol. Okay, right? So I think that is about Cannizzaro reaction. Anything else I'm missing? Rosenmund is okay.
Cross Cannizzaro, sir.
Cross Cannizzaro. Okay. Do you have cross Cannizzaro? And they'll not give the mechanism, but they'll have cross Cannizzaro. Oh my God. Great. Fine.
Sir, I think in NCRT we don't have cross Cannizzaro.
Yeah, even that's what I think. I think it's not there in the syllabus, cross Cannizzaro. Because for you to understand cross Cannizzaro, you have to understand the mechanism. I don't think NCRT will are that stupid to ask you that. Okay, I don't think you have. Okay, fine. Next thing I think is Etard. Etard reaction is there. Okay, fine. We'll look into it next. So next thing I can look at is Gataman Koch reaction, right? So I know what happens in Gataman Koch. I hope you know. I have benzene with HCl in the presence of CO. In the presence of copper 2+ ion, you are going to form benzaldehyde. Right? This is a famous way to prepare benzaldehyde, right? That's called, I think this reaction is there in NCERT, Gataman-Koch, right? So Gataman-Koch is like this. Okay. Okay, let me check. Etard reaction you have asked for. Yeah, we forgot actually one important stuff, but still, okay, we'll just look into it. Haloform fillings. Okay, cross aldol, cleansing chemical. I don't know why is it there. Okay, fine. So next one is Etard. Okay. So I don't know, I think the seventh one is Etard reaction. Okay, what converts to what here?
Toluene to benzaldehyde.
Sorry, toluene to benzaldehyde. Okay, what do you have to use here?
Chromyl chloride.
Good, right? CrO2Cl2. Am I right? Is this correct? CrO2Cl2?
Not sure about the formula.
Yeah, right. So it is CrO2Cl2. Okay, so that's what you have to use, and you have to do this. Now, if I ask you this compound getting, maybe I'll write here somewhere. So if I have to convert it into COOH, what I have to use here? Directly converting toluene to benzene carboxylic acid. What I have to use here?
KMNO4.
Absolutely right. You have to go for hot concentrated KMNO4. Okay, this is what is called as side chain oxidation, right? Now it doesn't matter how many carbon atoms you have. Even if you have 10 carbon atoms other than, if at all methyl, instead of that you have hexyl, say 6 more carbon atoms you had, then also the same compound will be formed. The other carbon atoms will go out as some other compounds. Okay, so irrespective of how many other carbon atoms you have, right? If you put KMNO4, you're going to end up in COOH, benzene carboxylic acid. Okay, and if at all you want to stop it at CHO, you have to use CrO2Cl. Okay,
Sir,
right.
if we have to attach the carboxylic group in the para or para position or something.
Yes, we have, right? So what do we do? That is, I think, is called Kolb's. That comes in phenols chapter, I guess. Right. So the reaction was something like this. Kolb's. So you had OH and you went for CO2, just CO2, and the presence of electricity. Obviously, I just have to put electron and stuff, right? So you'll have OH and COOH is going to come here, right? So this is possible, right? But if you want to have a CHO here, tell me, how can I do the conversion? Like what I want is this to get converted into this. Okay, right? So obviously, the ones you form, basically first you put COOH, you get formed here, done. But how will you convert this to this? Any mechanism or any steps you can think of? Anybody can answer this question. What is the time? Am I overshooting? I have 5 minutes. Okay. Okay, so we don't have time, so maybe I'll answer this. Okay, so first what I'll do is I will put this. Okay, basically first step is this. This is the first step. Okay, now from this I put zinc dust. So what will happen if I put zinc dust? I have a phenol and I put a zinc and I correct. I'll be removing the OH and I'm gonna form benzene. Right. So this OH is removed. Right. So all I have is the COOH. Okay. Now next what will I do is I can go for this one. Say I can go for CH3. Guys, I think I'll drop this part. I hope what you know what is this thing. I don't have space, so I'm just writing it from the first. Okay. Fine. So I had OH first, or I can directly go for first elimination of this one, zinc dust. But I cannot put COOH. No, I can put COOH, not a big deal, right? So I go for zinc dust. So you form benzene, and from benzene, say now I have to put, let me go for CH3Cl in the presence of AlCl3, Friedel-Crafts alkylation, right? RCl in the presence of AlCl3. So you know you're going to get R here, right? So now this is gonna become CH3, right? Now just now you went for Etard reaction, right? Etard reaction you can go, that is CrO2Cl2. What will you form is CHO, right? Now you can go for Coles CO2 in the presence of electron. You form CHO and COH. Done.
Sir, so what's the name of that compound, sir?
Which compound?
The final product with CHO and COH. Yes.
This is salicylic acid, right? Oh, that is OH and CHO. Oh, no,
yes, sir.
This doesn't have any name. This doesn't have any common name. You can give the IUPAC name if you want, but that doesn't have any common name.
Okay, sir.
Okay, right? Fine. So this you can do easily. Okay, right? Fine. And okay, we are talking about name reactions, so that will continue. Okay, this is a good question, right? I think this. So like this only have to work, people. It's not about knowing the reactions. You have to take as many as conversions as possible and you try to solve them. Okay, right? And if at all you are not able to get, maybe make a group for yourselves. Yeah.
Sir, the purpose of zinc dust is exactly what, sir?
Okay, fine. That's a good question. So what happens here is this zinc, I have a lone pair. Basically, this lone pair will be donated to zinc. So you're going to form something like OZN. Okay, and what happens is this will make the benzene ring more polarized in the sense that this will go and attack here and this bond leaves, something like that. That's what is going to happen, right? But again, it's a very complex mechanism. You don't have to worry about it, right? The role of the zinc is just to form a zinc is basically Lewis acid. Okay, if at all you want the perfect answer, zinc is going to act as a Lewis acid. So you know Lewis acid can accept a lone pair of electron. So the lone pair of electron is coming from oxygen, which is going to accept. That's all you need to know. Okay.
Yes, sir. I had another doubt. Like the thing is, from toluene, sir, like we have to attach COH group directly attached to the CH3, sir. Like not replacing the CH3 as such.
So you want this to get converted to this?
Sir, this one and also like directly attached to the CH3 also. Like
in the sense that say this to this?
Yes, sir. Yes, sir.
Okay, fine. Well, what do you want? You want this one or this one? Conversion.
The second one.
This one. Second one. Okay, we'll try to do the conversion. Okay, cool. Right. And guys, I think I will take next class half also to be this chapter only. I will tell the management, maybe we'll have some extra class. Are you guys free in the morning?
Yes, sir.
I know you have schools. You are going for schools. Okay, fine. Let me talk with Raghav and I'll get you back. Right, fine. Anyways, we'll speak about it later. We'll concentrate on this now. Okay, so this getting converted to this. Okay, so first what I can do, very simply I can do that actually, right? So first thing what I'll do is I will go for Cl2 bar H nu. Okay, so if I go for Cl2 bar H nu, what will happen? You'll have CH2Cl, right? One hydrogen removed, one chlorine getting added. This is your termination, that propagation, all these steps, right? That reaction. Okay, now next thing what I'll do is I'll put KCl. Okay, if I put KCl, what will happen? Nucleophilic substitution, Cl minus will be replaced by Cn minus. So I'll get CH2Cl. My problem is done. Go for hydrolysis. H3O plus, you're going to form CH2COH. Very simple. I know this is an acid derivative, right? Cyanides or any other stuff, any acid derivative on hydrolysis will give me acid, right? So first step, putting a chlorine here and then making a nucleophilic substitution happening, Cn will come here and then hydrolysis, you will be ending up. Okay, makes sense?
Yes, sir. Yes, sir.
Okay, good. So guys, fine. So I think we have to stop here, right? It's almost, yeah, I have already crossed your time, right? See, this is a very big chapter actually. This aldehydes, ketones, carboxylic acid is a little big chapter. We have to study a little more. Okay, fine. We'll see what we can do. Okay, is there any other questions, Steve?
Sir, could you just say the first reaction also?
This one? Okay,
Yeah.
fine, easy. Okay, so that I would do like this. I will go for say CH COCl, HOCl. I can go for HCOCl. This is methyl what is it? Acid chloride of formic acid. Instead of CH3COCl, I go for HC double bond OCl in the presence of AlCl. This is what reaction? If I put RCOCl in the presence of AlCl3, what is the name of the reaction? It's not a name reaction, but still, it is actually a name reaction. What is it? Anybody knows? RCOCl in the presence of AlCl3.
Sir, is it Friedel-Crafts?
Friedel-Crafts? What?
Acylation.
Yes, right. This is Friedel-Crafts acylation. But I don't think this will work. I'll just get CHO here. Maybe, right? It will work. Right? So you will get CH3, and I know what I'm going to get. I'm going to get a CHO, and I can go for any oxidation to form COH. You have so many oxidizing agents, right? KMnO4, CrO3, Cr2, HCrO4, right? Any oxidizing agent you can use to form.
Sir, but
Okay.
then like in the para position
yeah.
also it will be formed, or only specifically
Yes,
in
para position also it will be formed because my CH3 is ortho para directed, definitely. So ortho product as well as para product both you will get. But in case of conversions, they won't worry about all that. You just have to show that this happens. That's it.
So in addition, if we are having para position also, it's not an issue, right?
Yeah, you can show that. You can just show that this product is getting formed along with this product, right? But as long as they in the question, in the answer, they see that what they want, they're gonna give you the marks. It's not a big deal. Yeah.
Yes, sir. Okay, sir.
Okay, right? I'm thinking, is there any other way of doing this? Putting a COOH directly. Okay, maybe we'll discuss it. You also think about it. Is there any other way of doing it from what you know? Maybe we'll discuss it in tomorrow's class. I think we have a class. Okay, fine, guys. Is there any other question you want to ask?
No, sir.
Sir, are we doing Aldehydes chapter tomorrow as well?
I'm thinking at least first 20-25 minutes, right? We have to do a lot of conversions. Like conversions are very, very important. At least you will get from organic chemistry, you will get 5 to 7 marks, right? You will get conversions, and we are not doing much conversions as far as this thing. You're asking me something, I'm teaching it, and then actually certain stuff we are learning. But conversions like this, we have to discuss. Or what we can do. Okay, fine. We'll think about it. Tomorrow you come to the class. Tomorrow we'll see what we can do. Okay, right? We'll decide
Yes.
it.
Yes, sir.
Okay, cool. Thank you so much, people. We'll meet again tomorrow. I'm ending the class. Okay.
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Thank you.